I first really understood diamonds at age 22 in a geology lab. I was holding a diamond sample, just a small one, nothing rare or expensive, and the professor handed me a piece of graphite, a pencil lead essentially, and said, "These are the same element. Carbon, that's it. Same atomic number, same number of electrons, same element that makes up most of your body, that exists in the air you breathe as carbon dioxide, that forms the sugar running through your bloodstream right now. Except this piece of carbon was the hardest natural material on Earth. The other was soft enough to mark paper." I remember thinking, if the same element can be both of these things, what determines which one it becomes? The answer to that question is one of the most beautiful examples of how structure determines everything in the universe. It's not about the atoms themselves, it's about how they're arranged. And once you understand that, once you really see it, diamonds become something else entirely. Not just valuable because people decided they should be, valuable because they represent an almost perfect arrangement of matter, achieved under conditions so extreme that most of Earth's crust can't produce them. Carbon is peculiar. It's the fourth most abundant element in the universe, but it behaves differently from almost any other element. It doesn't like being alone. It doesn't like being simple. It wants to connect, to combine, to arrange itself in intricate patterns. This is because of how its electrons are organized. Carbon has 6 electrons, 4 in its outer shell. That outer shell wants 8, so carbon is constantly seeking out other atoms to share electrons with, to complete its stability. But here's where it gets strange. Carbon doesn't insist on the same arrangement every time. Depending on conditions, temperature, pressure, the presence of other elements, carbon will organize itself in completely different ways. We call these different arrangements allotropes, and carbon has more allotropes than almost any element. There's diamond, the hardest. There's graphite, so soft it marks paper. There's graphene, a single sheet of carbon atoms so thin it's essentially two-dimensional, so strong it could theoretically hold up a car hanging from a fishing line. There's graphite foam, where carbon atoms arrange themselves in a three-dimensional honeycomb, lighter than styrofoam but stronger than steel. There's amorphous carbon, which is disorganized, lacking any regular structure. There's carbon nanotubes, which are cylinders of carbon atoms rolled so tightly they're as hard as diamond, but sometimes more flexible. There's Buckminster fullerene buckyballs, where 60 carbon atoms arrange themselves in a soccer ball pattern, all the same element, all different structures, all different properties. This is the fundamental insight. Structure determines properties. This is why diamonds found near the surface are still diamonds, even though, in theory, they should have converted to graphite. The transformation from one crystal structure to another requires the atoms to rearrange, and that rearrangement takes time. Diamonds are metastable. They're in a different form than what's most stable, but the transformation is so slow that diamonds persist for billions of years at Earth's surface. The result? Kimberlite eruptions bring diamonds to the surface where they can be mined. And the diamonds that survive the journey are often the hardest, most perfect ones, the ones formed under the most intense pressures deep in the mantle. For centuries, diamonds were only available if you could find them, which meant mining, which was difficult and expensive. Then, in 1954, scientists at General Electric made a diamond in a laboratory. They did it by recreating the conditions that exist in the Earth's mantle: extreme pressure and temperature. They used a press that could generate pressures comparable to those 150 kilometers below the surface and temperatures around 1,600 degrees Celsius. They placed carbon, in the form of graphite, in this high-pressure, high-temperature environment, and it converted to diamond. The diamonds they made were small, industrially oriented, useful for cutting and grinding, but not gem quality. But the principle was proven. diamonds could be made in the lab. Since then, the technology has improved dramatically. A modern laboratory diamond synthesis uses two main methods: high pressure, high temperature, HPHT. Synthesis is the direct approach, essentially doing what GE did, but with better equipment and better understanding. You place carbon in a press, apply pressures of about 5 to 10 gigapascals, that's 50 to 100,000 times atmospheric pressure, heat it to 1,400 to 2,000 degrees Celsius, and diamond forms. These diamonds can be large, up to several carats for industrial use, sometimes larger. They can be high quality. The process is expensive because maintaining those conditions requires sophisticated equipment and consumes enormous amounts of energy. But for industrial applications, it's economical. An industrial diamond might cost millions in a press to make, but if it lasts 10 times longer than the previous diamond tool you were using, it pays for itself. Chemical vapor deposition, CVD, is more elegant. Instead of crushing carbon with a press, you expose a substrate, thin surface to grow on, to a carbon-containing gas, typically methane, at lower pressures and temperatures. You also expose it to some kind of energy source, usually microwave radiation, sometimes laser. This energy breaks down the methane molecules. The carbon atoms are now very reactive, and they preferentially form diamond structure on the substrate, building up layer by layer. CVD is slower than HPHT. It builds diamond gradually rather than forming it all at once under pressure, but the diamonds it produces can be incredibly high quality. And because it works at lower pressures and temperatures than HPHT, it uses less energy. It's become the dominant method for producing large, high-quality laboratory diamonds for both industrial and gemstone use. The CVD process is also where the real insight into diamond formation comes through. As the method has improved, scientists have discovered what makes diamond form preferentially rather than graphite. It turns out to be about the proportion of hydrogen radicals, hydrogen atoms missing an electron, in the gas phase. Hydrogen radicals attack graphite-like carbon structures and remove those carbon atoms, preventing graphite from accumulating. Meanwhile, diamond structure is more resilient to hydrogen radical attacks, so it builds up. This is essentially using chemistry to select for diamond over other carbon forms. The result is that laboratory-made diamonds are often higher purity and higher quality than natural diamonds. A natural diamond might have inclusions, defects, or impurities that form during its time in the mantle. A laboratory diamond can be made nearly perfect, perhaps with a level of impurities and defects controlled to specific purposes. For industrial uses, cutting, grinding, polishing, heat sinks for electronics, semiconductor wafers, laboratory diamonds have largely replaced natural diamonds. It makes no sense to use rare, expensive natural diamonds when you can make perfect industrial diamonds in the lab for a fraction of the cost. For gemstones, the situation is more complex. Laboratory diamonds and natural diamonds are chemically identical. A laboratory diamond is a real diamond, just made in a reactor instead of in the mantle. But there's a market distinction. Some people want natural diamonds. The story of the diamond formed 1 billion years ago deep in the earth appeals to them. Others prefer laboratory diamonds. They're often more affordable, environmentally friendly, no mining, and ethically sourced, no conflict diamonds. But chemically and physically, they're the same. The lab-grown diamond is diamond. It has the same hardness, the same optical properties, the same everything. Now let's get into why diamonds' properties are so extreme, because they all come back to structure, hardness, and strength. Diamond's hardness comes from the strength of carbon-carbon bonds and the rigidity of the structure. Carbon-carbon single bonds, the bonds in diamond, have a bond energy of about 350 kilojoules per mole. That's one of the strongest single bond energies. For comparison, hydrogen-hydrogen bonds, HH, have an energy of about 435 kilojoules per mole, stronger per bond, but there are no HH bonds in common materials. Most common bonds, like the CH bond in organic molecules or the OH bond in water, are weaker with bond energies of 200 to 300 kilojoules per mole. So diamond bonds are among the strongest. But what makes diamond hard isn't just strong bonds, it's the three-dimensional network. Every carbon atom is bonded to four others with no weak points. To deform diamond, you'd need to break these strong bonds. Under normal conditions, that requires enormous force. The energy barrier to break these bonds, to rearrange the atoms, is so high that diamond simply won't deform. It stays hard. But here's a subtle point. Under extreme pressure, even diamond can break. If you apply pressures exceeding those in the mantle, eventually diamond's structure breaks down. Scientists have observed this in laboratory experiments using diamond anvil cells, devices that use diamond itself as an anvil to create even more extreme pressures. At pressures beyond about 500 gigapascals, diamond structure destabilizes and transforms into other carbon phases, metallic carbon, amorphous structures, exotic phases that only exist under extreme pressure. But at any pressure that exists naturally on Earth, diamond is the hardest material. This makes it invaluable for cutting and grinding applications. Diamond saw blades can cut through granite, concrete, and other hard materials that would dull conventional steel blades. Diamond-tipped drill bits can drill through rock far more efficiently than steel. Diamond abrasives can polish and grind almost any material to fine tolerances. Thermal conductivity. This is where diamond structure produces something almost magical. The rigid lattice allows heat energy to propagate through it with almost no resistance. Heat travels through diamond in the form of phonons, quantum mechanical vibrations of the atoms. Because the atoms are so tightly bonded and regularly arranged, these vibrations propagate efficiently through the structure. The thermal conductivity of diamond is around 2,000 watts per meter Kelvin compared to copper at 400 watts per meter Kelvin and aluminum at 250 watts per meter Kelvin. Diamond conducts heat about 5 times better than copper, one of the best metallic heat conductors. This is why diamond is becoming critical for high-power electronics. Modern processors generate enormous amounts of heat in tiny spaces. Intel and other chip manufacturers have been experimenting with diamond heat spreaders and diamond substrates for high-power electronics. A diamond layer can conduct heat away from a hot processor chip and distribute it to a heat sink much more efficiently than conventional materials. The future of computing might depend on diamond's thermal properties. As we push toward more powerful processors and higher density circuits, thermal management becomes the limiting factor. Copper works up to a point, but it has limits. Diamond doesn't hit those limits. Optical properties and the sparkle. Diamond's beauty comes from its optical properties, which again emerge from its structure. Diamond has a very high refractive index, about 2.42 compared to glass at 1.52. This means light bends significantly when it enters or leaves a diamond. This bending creates the characteristic sparkle. Light enters the diamond, bounces around inside, and exits at different angles, creating flashes of light. But there's more. Diamond also has significant dispersion. Different wavelengths of light, different colors, refract at slightly different angles. This creates the fire of a diamond, the spectral spread of colors that you see when you look at a diamond under light. Red light bends slightly differently than blue light, so white light gets separated into its component colors. A well-cut diamond optimizes these optical properties. The facets of a cut diamond are positioned to maximize light entering the diamond, bouncing around inside, and exiting while also separating light into its component colors. The result is the characteristic brilliance and fire of a diamond gemstone. This is why diamond cutting is both an art and a science. The facets are positioned at precise angles, typically 58 for the crown, 33 for the pavilion, to optimize the optical path of light through the diamond. Change the angles slightly, and the sparkle changes. The best diamonds are cut to maximize the light returning to the viewer's eye and the spectral dispersion that creates color. Electrical and semiconductor properties. This is where diamond's potential for the future is greatest. Pure diamond is an excellent electrical insulator. The electrons are locked in bonds, and there are no free electrons to carry current. But if you add impurities, introduce a few nitrogen atoms or boron atoms into the carbon lattice, you can change this dramatically. Nitrogen atoms have 5 electrons in their outer shell, 1 more than carbon. When a nitrogen atom substitutes for a carbon atom in the diamond lattice, that extra electron becomes mobile. It can move through the diamond structure carrying electrical current. This dopes the diamond p-type, adding positive charge carriers, holes from missing electrons. Boron atoms have 3 electrons in their outer shell, 1 fewer than carbon. When boron substitutes for carbon, it creates a missing electron, a hole. This hole can move through the lattice, acting like a positive charge carrier. This creates p-type doping. By controlling doping, you can make diamond into a semiconductor, a material that can be turned on and off to control current flow. Semiconductor diamonds can be used to make transistors, diodes, and other electronic components. The advantage of diamond semiconductors is the combination of properties: extreme thermal conductivity to remove heat from circuits, extreme hardness, so circuits can operate in harsh environments, high temperature, high pressure, radiation, wide band gap. The energy required to create a current-carrying electron, which allows diamonds to operate at higher voltages and temperatures than silicon. Silicon semiconductors, which dominate modern electronics, have been pushed to their limits. Silicon loses its semiconductor properties above about 200 to 300 degrees Celsius. Silicon can be damaged by radiation. Silicon has thermal conductivity about 5 times worse than copper. Diamond doesn't have these limitations. Diamond semiconductors can operate at temperatures exceeding 600 degrees Celsius. They can withstand extreme radiation. They conduct heat far better than silicon. They can handle higher voltages. This is why diamond electronics is an active area of research. While it's not ready to replace silicon in mainstream computing, the technology isn't mature yet, the production is expensive. It's essential for specialized applications. Power electronics for electric vehicles, high-temperature sensors for jet engines, radiation-hard circuits for space missions, extreme environment applications where silicon would fail. Going back to how diamonds form naturally, there's something profound about the geological story. Diamonds only exist because they form deep in the earth under extreme pressures that only exist in the mantle. They only reach the surface because of rare, deep-sourcing magmas that bring them up before they can transform back to graphite. They're only found in specific locations where Kimberlite eruptions have occurred. The oldest diamonds ever found are about 3.8 billion years old, nearly as old as Earth itself. They formed in the deep mantle when Earth was young. They've been brought to the surface over the last few million years by Kimberlite eruptions. Some of them have been in human museums for only a few hundred years. This means you can hold in your hand a physical object that's older than most rocks on Earth's surface, that formed under conditions that don't exist at the surface, that was created by processes that happened a billion years before dinosaurs existed. There's something humbling about that. Diamonds form in specific regions of the mantle called cratons, ancient, stable regions of continental crust that have existed for billions of years. These regions are unusual. They're colder than the surrounding mantle, which makes them more likely to have stable mantle rocks and stable diamonds. They're stable, meaning they haven't been disrupted by earthquakes or major geological events for a long time. The deepest cratons extend down hundreds of kilometers. This is where diamonds form, in conditions so extreme that almost nothing else that forms there could survive at the surface. But diamonds brought up by rapid Kimberlite eruption do survive. They're the time capsules from the deep earth, the physical evidence of what exists kilometers below our feet. Diamond is entering a new era. For most of human history, diamonds were valued for beauty and rarity. In the 20th century, they became valued for industrial applications, cutting, grinding, polishing, thermal management. But in the 21st century, diamond is becoming essential for the future of technology. The thermal management applications are already here. Diamond heat spreaders are used in high-power electronics. As computing becomes more power-intensive and more compact, thermal management becomes more critical. Diamond will become standard in power electronics, heat sinks, and thermal interface materials. Diamond electronics, semiconductors made from diamond, is still developing. The technology isn't ready for mainstream computing, but it's getting there. Diamond transistors have been demonstrated. Diamond diodes have been demonstrated. The challenge now is scaling up production, reducing cost, and achieving the material quality and consistency needed for reliable electronics. Quantum computing might be where diamond becomes essential. Some approaches to quantum computing use defects in diamond as quantum bits, the fundamental units of quantum information. Nitrogen vacancy centers in diamond, places where a nitrogen atom sits next to a missing carbon atom, can be used as qubits that maintain quantum coherence for useful periods of time. These might become the basis for practical quantum computers. Diamond optics is another frontier. Because diamond is transparent to both visible and infrared light and conducts heat well, it could be used for windows in extreme temperature applications, spacecraft, furnaces, high-temperature reactors. Because it's the hardest material, it could be used for protective coatings on lenses and optical elements. Diamond biosensors are being researched. Because diamond can be doped to have specific electrical properties, and because it's biocompatible, it could be used to make sensors that detect biological molecules, useful for medical diagnostics, environmental monitoring, and then there's the wild card, quantum applications. At extremely low temperatures, defects in diamond exhibit quantum behaviors that could be useful for quantum computing or quantum sensing. The spins of electrons at these defects can be manipulated and measured, potentially creating quantum devices with practical applications. All of this flows from the same principle. Structure determines properties. The tetrahedral bonding of diamond creates a material with extreme hardness, extreme thermal conductivity, transparency, electrical properties that can be controlled through doping, and quantum properties at the defect level. If you understand the structure, you understand why diamond is valuable in all these different ways. This brings us back to where we started. The question of how the same element can be both diamond and graphite, and what determines the difference. The answer is pressure and temperature. At low pressures and temperatures, like those at Earth's surface, graphite is thermodynamically stable. Carbon prefers to arrange itself in flat layered sheets. This is the lowest energy configuration at surface conditions. At high pressures and temperatures, like those in the deep mantle, diamond is thermodynamically stable. Carbon prefers to arrange itself in a three-dimensional tetrahedral lattice. The transition happens at a pressure and temperature threshold. This threshold is mapped in what's called a phase diagram, a plot showing which crystal structure is stable at different pressures and temperatures. The diamond-graphite phase boundary lies roughly at the conditions of the Earth's mantle. Diamond is stable at the pressures and temperatures found at depths of 120 to 200 kilometers. Graphite is stable at shallower depths. But here's the crucial point. Once diamond forms at depth, it doesn't spontaneously convert back to graphite when you bring it to the surface. This would require the atoms to rearrange, to break carbon-carbon bonds, and form new ones in a different arrangement. This rearrangement is extremely slow. At room temperature and atmospheric pressure, the conversion from diamond to graphite would take an incomprehensibly long time. Not millions of years, but more like trillions of years or longer. so diamond is metastable at the surface. It's in the wrong form for the current conditions, but the transformation is so slow that diamonds persist indefinitely. This is actually common in chemistry. Many substances are metastable. They're in the wrong form for the current conditions, but the transformation is so slow that they persist. Diamonds are just the most famous example. Graphite, by contrast, is stable at Earth's surface. It doesn't need to be kept cold or protected. It will persist indefinitely because it's in the thermodynamically favored form at surface conditions. Interestingly, if you could compare a piece of graphite and a piece of diamond in the deep mantle, the graphite would be unstable. It would slowly convert to diamond. The same element, same pressure and temperature, but graphite would be the metastable phase and diamond the stable phase. This phase relationship between diamond and graphite is one of the most elegant examples of how pressure and temperature determine structure and how structure determines properties. The story of carbon allotropes extends beyond diamond and graphite. Graphene is a single sheet of graphite, just one layer of carbon atoms. It's been a subject of intense research since its isolation in 2004. Graphene is incredibly strong for its weight, more than 100 times stronger than steel. It's transparent, conducts electricity better than copper in some conditions, and conducts heat even better than diamond in its in-plane direction. The fascinating thing about graphene is that it's essentially a two-dimensional material. It has length and width, but is only one atom thick. This creates quantum mechanical effects that are unique to 2D materials. Carbon nanotubes are cylinders of carbon atoms, essentially rolled up graphene. They can be single-walled, one cylindrical layer, or multi-walled, multiple layers. Carbon nanotubes combine properties of graphite and graphene. They're as hard as diamond in some directions. They conduct electricity. They conduct heat. Carbon nanotubes were initially heralded as revolutionary materials that would transform every industry. Hype aside, they've found real applications in sports equipment, in electronics, in composite materials, in research applications. They're not as transformative as initially promised, but they're genuinely useful. Buckminster fullerene, C60, also called a buckyball or buckball, is a molecule made of 60 carbon atoms arranged in a soccer ball pattern. It's actually a discrete molecule, 60 atoms forming a closed shell, rather than an infinite crystal structure like diamond or graphite. Buckyballs were a sensation when they were discovered, and they found applications in semiconductor research and in chemical experiments. Amorphous carbon is carbon without a regular crystal structure. It's what you get if you deposit carbon atoms randomly without letting them organize into an orderly structure. Coal is mostly amorphous carbon, with some ordered regions. Soot is amorphous carbon. Amorphous carbon is used in various applications, coatings, friction materials, but it lacks the special properties of ordered carbon forms. Carbon nanofoams are three-dimensional structures of carbon atoms organized in an open network, like three-dimensional sponge. They're extremely light and can have unusual mechanical and thermal properties. What's remarkable is that all of these, diamond, graphite, graphene, carbon nanotubes, buckyballs, amorphous carbon, carbon nanofoams, are the same element arranged in different ways. Each has different properties emerging from its structure. Each is useful for different purposes. Carbon has more allotropes than any other element. This is because carbon's ability to bond in different ways, to create structures with different dimensionalities, 3D in diamond, 2D in graphene, 1D in nanotubes, molecular in buckyballs, leads to an extraordinary diversity of structures. Understanding carbon's allotropes is like understanding the alphabet of materials. If you understand the principle that structure determines properties, you understand why these different allotropes exist and why each is useful for specific applications. Beyond jewelry, diamonds have transformed industry, machining and grinding. Diamond tools are used to machine semiconductors, to grind precision optical elements, to cut through granite and concrete in construction. A diamond saw blade can cut through materials that would dull a steel blade in seconds. The reason is simple. Diamond is harder than almost anything you'd want to cut. Only diamond on diamond or specialized ceramic or super hard materials can scratch diamond. The efficiency gains are enormous. A diamond blade lasts much longer than a steel blade, so even though the initial cost is higher, the cost per cut is much lower, and the precision is better. A harder tool maintains its edge longer, so the cuts are cleaner and more precise. Polishing and lapping. Diamond abrasives are used to polish optical elements, to finish semiconductor wafers, to polish gemstones and glass. Diamond paste. Diamond particles. Embedded in a wax or oil matrix, is used for final polishing steps that require extreme precision. Thermal management. Diamond heat sinks are used in high-power electronics, particularly in applications where the thermal conductivity of copper or aluminum isn't sufficient. Companies like Intel and Raytheon have incorporated diamond thermal spreaders into advanced chips. As processors get more powerful and more compact, these applications will become more common. Cutting-edge research instruments. Diamond anvil cells use diamonds as ultra-high pressure anvils. Scientists can place material between two diamonds and squeeze them together to create pressures exceeding millions of atmospheres. These pressures allow study of matter under extreme conditions, conditions similar to Earth's mantle or the cores of planets. Diamond can withstand these pressures, making it ideal for this application. Oil drilling. Diamond-impregnated drill bits are used for deep oil drilling. The extreme hardness of diamond means the bits stay sharp much longer than conventional steel bits, and can drill through harder rock formations that would defeat steel bits. The speed and efficiency gains make diamond bits worth the high cost. Semiconductor processing. Diamond is being used in semiconductor processing equipment, parts that need to be extremely hard and wear resistant. Diamond-coated tools are used for polishing wafers, for cutting, for other precision machining steps. The industrial value of diamonds is enormous. Billions of dollars worth of industrial diamonds are used every year, mostly in applications where the extreme hardness, thermal conductivity, or other extreme properties of diamond are essential, and increasingly, laboratory-grown diamonds are dominating the industrial applications. A naturally mined diamond brings with it the cost of mining, the environmental impact, ethical concerns about conflict diamonds. A laboratory-grown diamond produced for a fraction of the cost, grown to whatever specifications are needed, is more economical for industrial use. Diamond is at the threshold of a transformation. For centuries, its value was primarily in jewelry. In the 20th century, it became valuable for industrial applications. In the 21st century, it's becoming valuable for advanced technology, heat management in electronics, quantum computing, high-temperature sensors, quantum biology applications. The bottleneck now is production and cost. Laboratory diamond production has advanced dramatically, but it's still not cheap enough to use for many potential applications. A diamond heat spreader for a high-powered chip still costs more than conventional heat spreaders. Diamond electronics are still in the research phase, but these challenges are being addressed. As production methods improve, as economies of scale kick in, diamond applications will expand. There's also the question of engineered properties. We can now grow diamonds with specific properties, specific impurities, specific defects, specific optical properties. This allows engineering diamonds for specific applications rather than just using natural diamonds or generic laboratory diamonds. And then there are the wildcard applications, quantum computing, quantum sensing, biomedical applications that could transform the value and relevance of diamond. One thing is certain, we've only begun to explore what diamond can do. The atomic structure that makes diamond the hardest natural material also makes it thermally conductive, semiconducting, optically useful, and potentially useful for quantum applications. As we develop better ways to grow diamond, better ways to engineer its properties, and better ways to use its properties, diamond will become as central to technology as silicon is now. The same atomic structure, carbon atoms bonded in a tetrahedral lattice, that makes diamonds precious gemstones is also the foundation for technology that hasn't even been invented yet. I started this journey with a professor showing me that diamond and graphite are the same element. That observation transformed how I thought about matter. It made me realize that asking, "What is this?" isn't enough. You have to ask, how are its atoms arranged? Because that arrangement determines everything. Carbon's willingness to arrange itself in radically different ways, in sheets, in three-dimensional lattices, in cylinders, in spheres, in amorphous formations, gives us a window into a fundamental principle of chemistry and physics. The same element, different structures, radically different properties. Structure determines properties. Arrange the atoms one way and you get something that marks paper. Arrange them another way, and you get the hardest material on Earth. This principle extends far beyond carbon. Every material we know is just atoms arranged in a specific way. Proteins are arrangements of atoms that create machinery doing essential work in your cells. Semiconductors are arrangements of atoms that conduct electricity in controlled ways. Crystals are arrangements of atoms that create materials with specific properties. Understanding this principle, that structure determines properties, is the foundation for understanding material science, for engineering new materials, for imagining what might be possible if we could arrange atoms exactly the way we want. And diamonds, in their pristine geometric perfection, in their extreme hardness and thermal conductivity, in their optical beauty and quantum properties, are the physical embodiment of this principle. Every diamond is a reminder. The structure of matter determines what matter can do. To truly appreciate diamonds' properties, we need to look more carefully at how the atoms actually fit together. The diamond cubic crystal structure is actually more complex than a simple tetrahedral lattice. Its two interpenetrating face-centered cubic FCC lattices offset from each other by 1/4 of the diagonal of the cube. This might sound abstract, but the result is that each carbon atom has 4 nearest neighbors arranged tetrahedrally around it, with no neighbors closer than the 4 tetrahedral neighbors. The distance between carbon atoms in diamond is 1.54 angstroms, about 0.000000154 meters. That's incredibly small. To give you scale, the period at the end of a sentence is roughly 500,000 angstroms wide. A single carbon atom in diamond is about 1/10,000,000th the diameter of that period, but the bonds connecting them are strong. A carbon-carbon single bond in diamond has a bond dissociation energy of about 350 kilojoules per mole. This means you need to supply 350 kilojoules of energy to break 1 mole, 6.022 times 10 to the 23rd power, of these bonds. That's about 5.8 times 10 to the minus 19 joules per bond, an enormous amount of energy for a single atomic interaction. For comparison, the thermal energy available at room temperature, KT, where K is Boltzmann's constant and T is temperature, is only about 4 times 10 to the minus 21 joules. The carbon-carbon bond in diamond is roughly 150 times stronger than the available thermal energy at room temperature. This is why diamond doesn't spontaneously break apart. Thermal energy can't break these bonds. The structure has another interesting feature. The coordination number is 4. This means each carbon atom is surrounded by 4 nearest neighbors. This tetrahedral coordination is actually quite common in nature. It appears in silicon, in germanium, in many semiconductors. But what makes diamond special is that the bonds are so strong and the lattice is so rigid that the tetrahedral coordination doesn't lead to any defects or weak points. The crystal planes in diamond are also noteworthy. Diamond has distinct cleavage planes, directions along which the crystal naturally breaks if you apply pressure. The primary cleavage direction in diamond is the octahedral plane, 1-1-1 plane in crystallographic notation. This is why diamond often cleaves into octahedral fragments. The weakest bonds are along these planes, though even these are extremely strong compared to other materials. Diamond also has a specific pattern of defects and impurities that affects its properties. Pure carbon diamond is actually quite rare. Most natural diamonds contain trace amounts of nitrogen, boron, hydrogen, and other elements incorporated during formation in the mantle. These impurities can drastically change diamond's properties. Nitrogen in diamond is particularly common. Nitrogen atoms replacing carbon atoms can create what's called nitrogen centers. In certain configurations, nitrogen atoms can trap electrons, creating colored centers that give diamonds their color. Much of the color in natural diamonds, yellows, browns, and some rarer colors, comes from nitrogen defects. Boron causes blue diamonds, one of the rarest and most valuable diamond colors. A few boron atoms in the crystal lattice are enough to create the striking blue color. The Hope diamond, one of the world's most famous gemstones, is blue due to boron impurities. Hydrogen incorporated into the diamond can create various defects, some of which interact with light in ways that create different colors. The complexity of how impurities affect diamond properties is still being studied. The process of making diamonds has evolved dramatically, and understanding the different methods reveals a lot about how chemistry determines crystal structure. HPHT methods in detail. High pressure, high temperature diamond synthesis typically uses what's called a belt apparatus or a cubic anvil press. A cubic anvil press uses 6 tungsten carbide anvils arranged in a cube around a central chamber. When you close the 6 anvils together, they create enormous pressure in that central chamber, pressures exceeding 50,000 atmospheres. Inside the chamber, you place a carbon source, graphite, a metal catalyst, usually iron, nickel, or cobalt, and sometimes other materials depending on what you want to synthesize. You heat the chamber to 1,400 to 2,000 degrees Celsius. At these pressures and temperatures, carbon dissolves into the molten metal catalyst. As the system cools, the carbon precipitates out as diamond nucleates on a seed crystal, a small piece of diamond crystal that serves as a template for growth. The process is called the solvent catalyst method because the metal acts as a solvent for carbon, allowing it to transport carbon atoms to the growing diamond crystal. HPHT diamonds tend to be somewhat smaller than CVD diamonds, typically up to a few carats for quality diamonds, though some have been made larger. The process is relatively fast. Diamonds can grow in hours rather than days, but the process requires expensive equipment and consumes enormous amounts of power. One interesting aspect of HPHT is that it produces diamonds under conditions very similar to those in Earth's mantle. In a sense, you're recreating the mantle environment in a small chamber in the lab. Some scientists have speculated that understanding laboratory diamond synthesis might actually teach us about how natural diamonds form in the mantle. CVD methods in detail. Chemical vapor deposition works completely differently. Instead of creating extreme pressure and temperature, you expose a substrate to a mixture of gases at relatively low pressure, typically 0.1 to 100 atmospheres, and moderate temperatures, 600 to 1,200 degrees Celsius. Though this seems hot, it's much cooler than HPHT. The gas typically contains a carbon source, methane, CH4, and hydrogen, H2. You also introduce energy, either microwave radiation, hot filament, or laser, that breaks apart some of the molecules. Here's where the chemistry gets interesting. The energy creates radicals, atoms or molecules missing electrons, making them highly reactive. Hydrogen radicals attack sp2 bonded carbon, the type of bonding in graphite, stripping those atoms away. This selective etching removes graphite-like structures. Meanwhile, sp3 bonded carbon, the type in diamond, is more resistant to hydrogen radical attack. Diamond preferentially forms and accumulates. The result is that you build up diamond layer by layer, atom by atom. Growth rates are typically 0.1 to 1 micrometers per hour. To grow a 1-carat diamond, about 2 millimeters in diameter, you'd need weeks or months of continuous growth. But the diamonds that result can be incredibly high quality. CVD diamonds can be nearly perfect, with impurities and defects controlled to whatever level is desired. CVD diamonds can be made as transparent as water or doped with specific impurities to create specific colors. CVD has another advantage. It can grow diamond on various substrates. HPHT can only grow on a diamond seed. The diamond nucleates on that seed. CVD can grow on silicon, tungsten carbide, or even other materials. This allows you to create composite materials. Diamond on silicon, for example, that couldn't be created with HPHT. The disadvantage of CVD is speed and cost. The slow growth rate means you need to run reactors for weeks at a time to produce a single diamond. The energy consumption is high. The equipment is complex. For industrial applications where you need many diamonds, CVD is expensive compared to HPHT. But for high-quality diamonds, for engineered properties, for research applications, CVD is increasingly dominant. Plasma-assisted CVD. In plasma-assisted CVD, the gas is partially ionized by a plasma, a state of matter where atoms are stripped of electrons and become reactive ions. This creates even more reactive species than standard CVD, which can lead to faster diamond growth. Plasma-assisted CVD can produce diamonds faster than standard CVD, though the quality might be slightly different. Microwave plasma CVD. This is the most commonly used CVD method for commercial diamond production. Microwave radiation creates a plasma in the gas mixture with growth rates of 0.1 to 1 micrometer per hour. The microwave plasma is contained and stable, making the process reliable and scalable. Seeding and nucleation. One challenge in diamond synthesis is nucleation, getting diamond to start growing. HPHT uses a diamond seed, so nucleation isn't a problem. CVD typically uses a diamond seed as well, though seeding isn't strictly necessary. Diamonds can nucleate spontaneously on various substrates, but seeding produces higher quality diamonds and more consistent growth. There's interesting science around seeding. The structure of the seed diamond affects how the new diamond grows. The orientation of the seed, the purity of the seed, the quality of the seed surface all influence the quality of the diamond that grows on it. For industrial diamonds, seeding with a high-quality diamond produces better diamonds. But high-quality seeds are expensive. For mass production, cheaper, lower-quality seeds might be used, which will produce lower-quality diamonds. This is why engineered industrial diamonds are often produced with multiple quality tiers, depending on the seed quality and other parameters. Post-growth treatment. After diamonds are synthesized, they often require post-growth treatment. HPHT diamonds might be annealed, heated under specific conditions, to improve their properties. CVD diamonds might be polished, etched, or treated to achieve desired optical properties. The cutting of diamonds, producing the facets that make a gemstone sparkle, is also a specialized process. For industrial diamonds, cutting might be minimal. For gemstones, cutting is complex and precise, with each facet positioned at exact angles to optimize the optical properties. For centuries, diamonds were valued purely for their beauty and rarity. But in the modern era, diamonds have become tied to serious environmental and ethical concerns. Conflict diamonds. The term conflict diamond refers to diamonds mined in war zones and sold to finance armed conflict. From the 1980s through early 2000s, significant diamond mining in Angola, Sierra Leone, and other countries helped finance brutal civil wars. Diamonds were used as a portable currency to buy weapons and supplies for fighting groups. The ethical issue was profound. People were wearing diamonds on their hands without knowing they were wearing a symbol of war, slavery, and atrocity. This awareness led to the Kimberlite Process Certification Scheme in 2003, an attempt to prevent conflict diamonds from entering the mainstream diamond market. The Kimberlite process created a certification system where diamonds could be traced to their source, and conflict diamonds could theoretically be excluded. In practice, the Kimberlite process has been criticized as ineffective. It's difficult to trace diamonds back to their exact origin. Diamonds can be mixed, moved between countries, laundered through legitimate supply chains. Many diamonds labeled as conflict-free through the Kimberlite process have come from questionable sources. The result is that the ethical status of natural diamonds remains ambiguous. Some diamonds are genuinely conflict-free. Others have questionable origins. It's difficult for consumers to know for certain. Environmental impact of mining. Diamond mining has significant environmental impact. Open-pit mining removes entire mountainsides to access diamond-bearing rock. The mining process requires enormous amounts of water, energy, and chemical inputs. Mining sites are often in pristine environments, rainforests, wildlife reserves, where the ecological impact is severe. The waste from diamond mining is enormous. To extract 1 carat of diamond, 200 milligrams, you might need to remove and process multiple tons of rock. Most of that rock is waste, leaving behind massive open pits, contaminated water, and disrupted ecosystems. Illegal and artisanal mining often has even worse. Environmental impact. Miners use mercury and cyanide to extract diamonds from alluvial deposits, diamonds in riverbeds or deposits, contaminating water sources and harming human health. Laboratory diamonds, as an alternative lab-grown diamonds, create an ethical and environmental alternative to mined diamonds. Lab-grown diamonds require no mining. They're produced in controlled facilities using existing technology. The energy consumption of CVD is high, but if powered by renewable energy, lab-grown diamonds become far more environmentally friendly than mined diamonds. Lab-grown diamonds have no conflict issues. They're produced in facilities where working conditions can be controlled and monitored. They're traceable from production facility to consumer. Lab-grown diamonds are also cheaper, often 30 to 50% cheaper than comparable mined diamonds. As production increases and technology improves, lab-grown diamonds will likely become cheaper still. The gemstone industry initially resisted lab-grown diamonds, promoting natural diamonds. But consumer attitudes are changing. Young consumers in particular are increasingly aware of the environmental and ethical issues with mined diamonds and prefer lab-grown alternatives. For industrial diamonds, the transition to lab-grown has already happened. Almost all industrial diamonds are now lab-grown because they're cheaper and have better controlled properties. For gemstones, the transition is happening more slowly but accelerating. Within the next decade, lab-grown diamonds will likely dominate the market for diamonds sold as gemstones. Interestingly, lab-grown diamonds and mined diamonds are chemically identical. The only difference is origin. A lab-grown diamond is a real diamond. It has the same crystal structure, the same hardness, the same optical properties. The only reason to prefer a mined diamond is sentimental. The story of a diamond formed billions of years ago in the mantle appeals to people. But from a scientific and practical perspective, lab-grown diamonds are superior. They're more ethical, more environmental, cheaper, and often higher quality. One of the most exciting frontiers for diamond is quantum applications. This is where defects in diamond, imperfections that would be undesirable for gemstones or some industrial applications, become valuable. Nitrogen vacancy centers. A nitrogen vacancy center is a defect in the diamond crystal. a nitrogen atom where a carbon atom should be, positioned next to an empty lattice site, a vacancy, a missing carbon atom. These defects have remarkable properties. An electron associated with the nitrogen vacancy center can exist in a quantum state, a superposition of multiple states simultaneously. The electron's spin, its intrinsic angular momentum, can be manipulated using radio frequency radiation and can be read out using fluorescence. This makes nitrogen vacancy centers useful as quantum bits, qubits, for quantum computing. A qubit can store information in a quantum superposition, allowing quantum computers to explore many possibilities simultaneously. Nitrogen vacancy centers are also useful for quantum sensing. The spin state of the electron is sensitive to magnetic fields, electric fields, and other physical quantities. By measuring the spin state, you can measure these quantities with extraordinary sensitivity. Applications of nitrogen vacancy centers include quantum computing. Diamond with nitrogen vacancy centers has been proposed as a platform for quantum computing. IBM, Google, and other technology companies have explored this approach. Magnetometry, measuring tiny magnetic fields, useful for neuroscience, measuring magnetic fields from neurons. Geophysics, measuring Earth's magnetic field at high resolution. Medical imaging. Timekeeping. The spin states have very precise frequencies, useful for creating atomic clocks. Other defect centers. Beyond nitrogen vacancy centers, diamonds can have other defect centers useful for quantum applications. Silicon vacancy centers. Silicon atoms replacing carbon atoms with adjacent vacancies. These also have quantum properties and might be useful for quantum applications. Germanium vacancy centers, similar to silicon vacancy. Group 4 centers. Defects involving other elements from group 4 of the periodic table. The science of engineering these defects, creating them with specific properties, at specific locations, in specific quantities, is advancing rapidly. The future of diamond quantum. The potential is enormous. Diamonds at room temperature can maintain quantum coherence. Quantum superposition states can persist longer than many other materials, which are typically cooled to near absolute zero. This makes diamond potentially more practical for quantum computing than alternative platforms. As the technology matures, diamond could become the basis for practical quantum computers. Extraordinarily sensitive magnetometers and sensors, precision timekeeping devices, medical diagnostic tools based on quantum sensing. All of this emerges from the defects in diamond crystal structure, defects that are being engineered and manipulated at the quantum level. We've discussed how diamonds form under extreme pressure and temperature in the mantle. But what happens to diamonds at even more extreme conditions? Static compression. Using diamond anvil cells, scientists can create pressures far exceeding those in the mantle. At pressures above about 400 gigapascals, 4 million times atmospheric pressure, diamond undergoes phase transitions. Its crystal structure changes. Different arrangements of carbon atoms become stable under these extreme pressures. One such phase is diamond-like carbon, or amorphous carbon phases that are stable only under extreme pressure. Some phases might be even harder than diamond, or have other unusual properties. These extreme pressure phases are important for understanding Earth's interior. At the core mantle boundary, pressures exceed 130 gigapascals. The carbon chemistry at these depths might involve phases we can only create artificially in the lab. Dynamic compression diamond can also be studied under dynamic compression, compression by shock waves, or high-velocity impacts. These studies simulate conditions in planetary collisions or in the cores of planets being formed. High-velocity impacts can create pressures and temperatures exceeding those of the mantle, transiently creating exotic carbon phases. Some meteorites contain exotic carbon phases that presumably formed during planetary collisions. Thermal stability diamonds are stable to extremely high temperatures. A diamond won't melt until temperatures exceed about 3,550 Kelvin, 3,280 degrees Celsius, hotter than the surface of the sun. But at high temperatures, diamonds can transform or graphitize. Graphitization, the conversion of diamond to graphite, happens faster at high temperatures, even though graphite is still thermodynamically unstable at these temperatures. The transformation is slow, but it does occur. This is why industrial diamonds used in high-temperature applications must be protected. A diamond cutting tool used for cutting granite at high speeds heats up due to friction. If the temperature gets high enough and the exposure is long enough, the diamond can convert to graphite and lose its hardness. Solutions include cooling the diamond cutting tool with water or oil, using coatings that protect the diamond surface, or using specialized diamond formulations that resist graphitization better. The semiconductor revolution started with silicon. Silicon's properties, particularly its ability to be doped to create p-type and n-type regions, enabled transistors, diodes, and complex integrated circuits. But silicon has limitations. Silicon's limitations. Silicon has a band gap energy of 1.1 electron volts. This means that at temperatures above about 300 Kelvin, 27 degrees Celsius, thermal energy starts creating unwanted charge carriers. Above about 200 degrees Celsius, silicon starts losing its semiconductor properties. For power electronics operating at high temperatures, silicon becomes unreliable. Silicon's thermal conductivity is only about 150 watts per meter. Kelvin. Good for a semiconductor, but not great for dissipating heat from high-power devices. Silicon also has limitations for high-voltage applications. Above certain voltages, silicon devices break down. This limits their use in high-voltage power electronics. Diamond's advantages: diamond has a much higher band gap, about 5.5 electron volts. This means thermal energy doesn't create unwanted charge carriers until much higher temperatures. Diamond semiconductors can operate reliably at temperatures exceeding 600 degrees Celsius. Diamond's thermal conductivity is 2,000 watts per meter, Kelvin over 10 times. Silicon's, which means heat is conducted away from the device extremely efficiently. Diamond can also handle higher voltages than silicon. The breakdown voltage, the voltage at which the material fails, is much higher for diamond. This allows diamond devices to handle higher power with smaller device sizes. Diamond semiconductor applications. These properties make diamond particularly valuable for power electronics. Diamond MOSFETs and diodes can handle higher power, higher voltage, higher temperature than silicon alternatives. RF, radio frequency. Electronics. Diamond transistors can operate at higher frequencies and higher power than silicon, useful for radar, communications, and other RF applications. Thermal management chips. Diamond heat spreaders and thermally conductive substrates conduct heat away from hot semiconductor junctions. Aerospace applications. Aircraft engines, avionics, and power management systems operate in high-temperature environments where silicon fails. Diamond semiconductors could be game-changing for aerospace. Geothermal and oil drilling. Sensors and electronics must operate at high temperatures deep underground. Diamond semiconductors could enable real-time monitoring in geothermal wells and oil wells. Automotive power electronics. Electric vehicles require efficient power electronics. And others are medicine. Structure determines properties. And diamond represents one of the most extreme examples of this principle. Its structure, carbon atoms in a perfect rigid three-dimensional lattice, every atom bonded to four others as tightly as those covalent bonds allow, produces properties that are extreme in multiple directions. To really understand diamond, you need to see its structure at the atomic level. Imagine a single carbon atom. It has 6 electrons, 4 in the outer shell that can form bonds. In diamond, that carbon atom forms 4 bonds, one with each of 4 neighboring carbon atoms. These bonds point toward the corners of a tetrahedron, a three-dimensional shape with 4 corners and 4 faces. Now imagine a second carbon atom at one corner of that tetrahedron. It has 4 bonds too, one pointing back to the first carbon atom and 3 pointing toward 3 other carbon atoms. Now imagine stacking these tetrahedra. Layer upon layer, each carbon bonded to 4 others, each tetrahedron sharing vertices with its neighbors, creating a three-dimensional lattice. This is the diamond structure. It's called the diamond cubic lattice, and it's one of the most efficient ways to pack atoms together while maintaining maximum connectivity. Every carbon atom is bonded to 4 neighbors. Every bond is a strong covalent bond. There are no weak points, no sheets that slide apart, no regions where atoms are loosely held. The structure is so regular and efficient that natural diamonds often grow into perfect octahedral shapes, 8-sided crystals, which is the natural form that this tetrahedral bonding produces. A perfect diamond crystal is a physical manifestation of atomic geometry made large. This perfection in structure produces the extreme properties we associate with diamonds. Hardness. Diamond is the hardest natural material on Earth. It can't be scratched by anything except another diamond. This is because there's no easy way to break the atomic bonds holding it together. To scratch diamond, you'd need to break carbon-carbon bonds, which requires enormous force. Only diamond with bonds of similar strength and hardness can do this. When we measure hardness using the Mohs scale, a scale from 1, talc, soft, to 10, diamond, hardest, diamond is alone at the top. It's not just 1 point higher than the next material on the scale, it's orders of magnitude harder. Corundum, the material that ranks 9 on the scale, which includes rubies and sapphires, can be scratched by diamond, but not by most other materials. Diamond sits at a different level of hardness entirely. Thermal conductivity. Diamond conducts heat better than any other natural material. This is because the rigid structure allows vibrations to propagate through it efficiently. When atoms are arranged in a rigid lattice with no defects, heat energy travels through them with almost no resistance. Diamonds are so thermally conductive that if you hold a diamond in your hand, it will feel cold to the touch because it draws heat from your skin so efficiently that your thermal sensors register it as cold. This thermal conductivity is actually why diamonds are becoming increasingly important in electronics and computing. As processors get smaller and generate more heat in less space, thermal management becomes critical. Diamond's ability to conduct heat away from hotspots is becoming essential for next-generation computing and power electronics. Optical properties. Diamond is transparent to visible light, but it's also transparent to infrared radiation, heat radiation. This makes it useful for optical applications where you need something that transmits both visible and infrared light. But more dramatically, diamond has an extremely high refractive index, meaning light bends significantly when entering or leaving a diamond. This is why diamonds sparkle the way they do. Light entering the diamond bends, bounces around inside, and exits at angles that create the characteristic flash and fire of a diamond gemstone. The refractive index is so high that a properly cut diamond displays what's called brilliance, the brightness of light reflected from the diamond, and fire, the spectrum of colors that appear in the diamond as light is dispersed. These properties emerge directly from the atomic scale structure. Electrical properties. This is where diamond becomes interesting in a counterintuitive way. Given how tightly bonded the carbon atoms are, you might expect diamond to be a good electrical conductor. It's not. Diamond is an insulator. It doesn't conduct electricity under normal conditions. This is because all the electrons are locked into bonds. There are no free electrons to carry current. But here's the trick. If you dope diamond, add impurities that create free electrons, or apply a strong enough electrical field, you can make diamond conduct electricity. In fact, diamonds doped with boron become semiconductors. They can be turned into electronic devices that control the flow of electricity. And because diamond conducts heat so well while semiconducting electricity, it's perfect for high power electronics that need to dissipate lots of heat while controlling current. This combination of properties, extreme hardness, extreme thermal conductivity, transparency, and the potential for high power electronics makes diamond valuable far beyond jewelry. And all of these properties flow from one thing: the tetrahedral bonding structure, where each carbon atom is connected to four others in a rigid, three-dimensional lattice. For diamond to form naturally, you need two things: carbon and extreme pressure and temperature. The carbon is abundant. It's present in the Earth's mantle, distributed throughout rocks, sometimes concentrated in carbonate minerals, sometimes present in organic material that's been buried deep. The extreme conditions are trickier. Diamonds don't form everywhere, and they don't form at shallow depths. They form deep in the Earth, specifically in the upper mantle, at depths of roughly 120 to 200 kilometers below the surface. At these depths, the pressure is intense, about 5 to 10 million times atmospheric pressure at Earth's surface. The temperature ranges from about 900 to 1,200 degrees Celsius. At these pressures and temperatures, carbon transitions from graphite, which is the stable form of carbon at lower pressures, to diamond. The high pressure forces the carbon atoms closer together, and the tetrahedral bonding of diamond becomes the most thermodynamically stable arrangement. But here's the interesting part. Diamonds don't stay at that depth. They don't make their way to the surface gradually over millions of years through geological processes. Instead, they ride up in kimberlite magma. Kimberlite is an unusual type of magma, extremely rare, extremely deep sourcing, originating from the mantle itself rather than from crustal melting. When kimberlite forms, it's hot enough and fluid enough to carry diamonds, and critically, it moves fast, very fast. Kimberlite erupts from the depths to the surface in a matter of hours or days, not over geological timescales. This speed is crucial because if diamonds were brought to the surface slowly, they'd transform back into graphite. Graphite is the stable form of carbon at the lower pressures near Earth's surface. It's only the extreme pressures of the deep mantle that make diamonds stable. Bring those diamonds up gradually, letting them reach equilibrium with the lower pressure environment, and they'd convert to graphite. But kimberlite moves so fast that diamonds don't have time to convert. They're essentially quenched, brought from high pressure and temperature to low pressure and temperature so quickly that the atomic structure remains locked in the diamond configuration, even though it's now thermodynamically unstable. Diamond has some surprising applications in biology and medicine. Biocompatibility. Diamond is biocompatible. It doesn't trigger immune responses in biological tissues. This makes it suitable for medical devices that need to be in contact with living tissue for extended periods. Biosensors. Diamond has been proposed for creating biosensors. The surface of diamond can be functionalized, modified to have specific chemical groups that bind to biological molecules. Electrodes made of diamond can detect the binding of these molecules, signaling the presence of specific biomarkers. Potential applications include disease diagnosis, detecting specific proteins or nucleic acids that indicate disease, environmental monitoring, detecting pollutants in water, food safety, detecting pathogens or contaminants in food. The advantage of diamond biosensors is that diamond is chemically inert. It won't react with the biological samples or interfere with the measurements. And its electrochemical properties can be engineered to be sensitive to specific molecules. Drug delivery diamond nanoparticles have been investigated for drug delivery. A drug could be attached to a diamond nanoparticle, which is then injected into the body and targeted to a specific location. The diamond carrier would be biocompatible and wouldn't trigger immune responses. Diamond nanoparticles are also useful for fluorescent labeling. If they contain nitrogen vacancy centers or other fluorescent defects, they can be used as fluorescent labels for imaging in biology and medicine. Medical implants diamond coatings have been proposed for medical implants. A titanium or steel implant coated with diamond would have the biocompatibility of diamond and the mechanical strength of the underlying metal. The challenge is that diamond is very hard, but also brittle. It can crack if subjected to shearing forces. So, diamond coatings work best for implants where the loading is not too severe. Neuroscience diamond microelectrodes with nitrogen vacancy centers could be used for detecting electrical activity in neurons with extraordinary spatial resolution. This could revolutionize neuroscience, allowing recording from large populations of neurons simultaneously with single-cell resolution. Understanding diamonds also means understanding their history in human culture. The first diamonds were known in India as early as the 4th century BCE. The earliest diamonds were found in alluvial deposits, diamonds in riverbeds and surface accumulations in India. These diamonds were collected by panning in rivers similar to gold panning. For thousands of years, India was the only source of diamonds. Indian diamonds were traded along the Silk Road to the Middle East and eventually to Europe. These diamonds were highly valued, worn by royalty and the wealthy. The diamond trade. In the 1600s and 1700s, Brazil became the world's major diamond source. Brazilian diamonds were found in alluvial deposits and mined using slave labor in brutal conditions. In the late 1800s, diamonds were discovered in South Africa and subsequently in other parts of Africa. The discovery of diamonds in South Africa transformed the diamond industry. Massive open-pit mines were opened. Diamond exploration became a major industry. Cecil Rhodes and the De Beers Consolidated Mines Company effectively monopolized the diamond trade from the 1880s through much of the 20th century. De Beers controlled the supply, the price, and the marketing of diamonds. The company created the cultural association between diamonds and love, engagement rings, and status. The De Beers monopoly. De Beers' control of the diamond market lasted for over a century. The company would buy diamonds from other suppliers, stockpile them to control supply, and release them in ways that maintained high prices. In the 1980s and 1990s, the monopoly began to break. Russian diamonds, Canadian diamonds, and other sources entered the market. De Beers' control weakened, and eventually the company left the business of controlling diamond supply. But the cultural association between diamonds and engagement rings created by De Beers marketing persisted. The concept of a diamond engagement ring, considered traditional and timeless, was actually invented by advertising in the 1930s to 1950s. Famous diamonds. Some diamonds have become famous for their size, beauty, or historical significance. The Hope Diamond, a deep blue diamond of 45.52 carats, famous for its color and for theorists, famous for its color and for the superstition that it carries a curse. It's displayed at the Smithsonian Institution. The Cullinan Diamond, the largest rough diamond ever found, 3,106.75 carats. It was cut into several large polished diamonds, including the Great Star of Africa, 530.4 carats, and the Second Star of Africa, 317.4 carats. The Koh-i-Noor, a diamond with a complex history, first mentioned in records in the 1300s, it passed between Indian, Persian, Afghan, and British hands. It's now part of the British Crown Jewels. Pink Star, a 59.60 carat vivid pink diamond, one of the most valuable diamonds in the world. These famous diamonds are remarkable not just for their size or beauty, but for their histories. the cultures they pass through, the people who possess them, the stories attached to them. The most valuable diamonds are often valuable not because they're bigger or prettier than others, but because of their history and provenance. A diamond with a known history from a famous collection or with historical significance commands a premium far exceeding what its physical properties would suggest. Diamond is the hardest natural material, but there are other materials that approach or match diamond in hardness under specific conditions. Cubic boron nitride, CBN. Cubic boron nitride is sometimes called synthetic diamond because it has a similar crystal structure to diamond but with boron and nitrogen atoms alternating instead of carbon atoms bonded to carbon atoms. CBN is the second hardest material known, with hardness approaching diamonds. It's slightly softer than diamond but much more thermally stable. Whereas diamond converts to graphite at high temperatures, CBN is stable to much higher temperatures. CBN is manufactured similarly to synthetic diamonds, using HPHT or CVD methods. It's used for industrial applications where high temperature stability is important, such as cutting and grinding cast iron and other difficult to machine materials. The interesting chemistry is that CBN has similar hardness to diamond despite being a different compound. The hardness comes from the similar tetrahedral bonding structure and strong BN bonds. Aggregated diamond nanorods. Under extreme pressures, over 40 gigapascals, carbon can form a structure called aggregated diamond nanorods. This material is predicted to be harder than conventional diamond and more thermally stable. Aggregated diamond nanorods have been synthesized in the lab in very small quantities, but scaling up production is challenging. If large-scale production becomes possible, aggregated diamond nanorods could be useful for extreme hardness applications. Wurtzite boron nitride. Another form of boron nitride called wurtzite has a hexagonal crystal structure, like graphite, but with strong BN bonding. Theoretical calculations suggest it might be harder than diamond, but experimental verification is difficult because it's very hard to synthesize and study. Sapphire, corundum. Sapphire is the form of aluminum oxide, Al2O3, that includes gemstones like rubies, red, and sapphires, blue. Sapphire is much softer than diamond, ranking 9 on the Mohs hardness scale compared to diamond's 10, but it's still very hard and is used for watch crystals, optical windows, and other applications requiring hardness and optical transparency. Carbon nanotubes and graphene. While not as hard as diamond in terms of resistance to scratching or indentation, carbon nanotubes and graphene have extraordinary strength-to-weight ratios. A nanotube or graphene sheet is stronger per unit mass than diamond, making it useful for applications where weight matters. The difference is that nanotubes and graphene are small-scale structures. Nanotubes are tiny cylinders. Graphene is a single layer. Building large structures with them is challenging. But for specific applications, aerospace composites, sports equipment, electronics, nanotubes and graphene are becoming important. The broader picture. Comparing different hard materials reveals that hardness comes from specific atomic arrangements and strong bonding. Diamond's tetrahedral bonding and three-dimensional lattice create hardness. CBN's similar structure creates similar hardness. Nanotubes' cylindrical structure creates different properties, high strength rather than hardness. Understanding the relationship between atomic structure and macroscopic properties is key to predicting and engineering new materials with desired properties. We mentioned that impurities and defects affect diamond color. Let's explore this in more detail. Nitrogen and yellow diamonds. Nitrogen is the most common impurity in natural diamonds. Depending on how nitrogen atoms are arranged and bonded, different colors result. When nitrogen atoms are isolated in the diamond lattice, they create yellow colors. These are called nitrogen centers, or N3 centers, depending on the specific configuration. Nitrogen-rich diamonds can be yellow, olive yellow, brown, or other colors. Many diamonds have some degree of yellowish tint from nitrogen. Boron and blue diamonds. Boron creates blue diamonds by a different mechanism than nitrogen creates yellows. Boron atoms in the diamond lattice can accept electrons from surrounding atoms, creating electron deficiencies, holes, that interact with light. To create blue color, true blue diamonds, like the Hope diamond, require boron concentrations of at least several parts per million. Boron-doped diamonds can be quite blue, deep blue, vivid blue, or lighter sky blue, depending on boron concentration and other factors. Hydrogen and brown diamonds. Hydrogen incorporated into the diamond lattice creates various defects that can produce brown colors. Brown diamonds are the second most common colored diamonds after yellows. The mechanism of brown color is still being studied, but it appears to involve hydrogen-related defects that interact with light. Radiation and green diamonds. Some diamonds are colored green by radiation. This can be natural radiation from radioactive elements in the surrounding rock or artificial radiation applied in the lab. Radiation creates lattice defects, displaced carbon atoms or other defects, that interact with light to produce green color. Green diamonds are rare in nature but can be created artificially. Structural defects and graining beyond chemical impurities. Structural defects in the diamond lattice affect its properties. Twinning, where the crystal structure changes orientation. Graining, localized changes in crystal orientation. And other defects create visual patterns in diamonds that gemologists note. Some diamonds have visible graining or twinning that creates visible planes or patterns in the crystal. This reduces the diamond's clarity and value. Fluorescence and color centers under ultraviolet light. Some diamonds fluoresce. They emit visible light. This fluorescence comes from defects in the crystal that absorb UV light and emit visible light. Common fluorescence colors are blue, yellow, and white. Some diamonds fluoresce quite strongly, others faintly. Fluorescence is used as a diagnostic tool by gemologists. It can help identify diamonds and distinguish natural from synthetic diamonds, though this isn't always reliable. The industrial diamond market is actually much larger than the gemstone market. Billions of dollars worth of industrial diamonds are used annually. Diamond saw. Blades. Diamond saw blades use diamond particles, typically synthetic, held in a metal matrix. The diamond particles do the cutting, while the metal holds them in place. Diamond saw blades are used for cutting granite, marble, and concrete in construction, slicing silicon and other semiconductors in manufacturing, precision cutting in laboratory and medical applications, cutting through reinforced concrete in demolition. A diamond blade can cut through materials that would completely dull a steel blade. This makes diamond invaluable for construction and manufacturing. Diamond grinding wheels. Similar to saw blades, diamond grinding wheels use diamond particles in a matrix. They're used for grinding precision optical elements, finishing semiconductor wafers, polishing gemstones and glass, finishing industrial parts to tight tolerances. Diamond's hardness allows grinding wheels to maintain their shape and cutting edge for much longer than conventional wheels, resulting in better precision and longer tool life. Diamond polishing and lapping diamond paste and slurry. Tiny diamond particles suspended in oil or water are used for final polishing steps. They can polish materials to extremely fine surface finishes, important for optics, semiconductors, and precision mechanical parts. Diamond coatings. Diamond coatings are deposited on tools, dies, and other parts to improve hardness and wear resistance. CVD methods are used to deposit thin diamond coatings on carbide tools, steel dies, and other substrates. A diamond-coated cutting tool can outlast an uncoated tool by 10 times or more, justifying the cost of the coating. Cutting and drilling. Diamond-impregnated cutting and drilling tools are used in oil and gas well drilling, diamond-impregnated drill bits, mining of minerals and metals, quarrying of stone, geological exploration, and core sampling. Diamond bits can drill through harder rock formations that steel bits can't penetrate, and they maintain their sharpness much longer than conventional bits. Wire saws. Diamond wire saws, steel wire embedded with diamond particles, are used to cut. Silicon wafers in semiconductor manufacturing. granite and marble in quarrying, concrete in construction. The advantage of wire saws is that they make very narrow cuts with minimal material waste, important for expensive materials like silicon or large stone. The economics of industrial diamonds. Industrial diamonds might be worth less per unit than gem diamonds, but the total volume is huge. A single oil well might use industrial diamond worth millions of dollars. Semiconductor manufacturing uses massive quantities of industrial diamonds. As a result, the industrial diamond market far exceeds the gemstone market in total value. And this is where the revolution to lab-grown diamonds has already happened. Nearly all industrial diamonds are now synthetic. Beyond current applications, there are frontier areas where diamond might play important roles. Diamond quantum computing. The use of nitrogen vacancy centers in diamond for quantum bits is an active area of research. Google and IBM have both explored diamond as a platform for quantum computing. The advantage is that diamond qubits can maintain quantum coherence at room temperature longer than many alternative approaches. Extreme temperature sensors. Diamond semiconductors and sensors could enable monitoring at temperatures where current technology fails. This would be valuable for jet engine monitoring, temperatures exceeding 1000 degrees Celsius, geothermal well monitoring, temperatures reaching 300 plus degrees Celsius, furnace and industrial heat process monitoring, space exploration, Mars rovers, deep space probes, space applications beyond temperature sensors. Diamond's properties could transform space exploration. Diamond windows that are tough enough to survive rocket vibrations, transparent to desired wavelengths, and radiation-resistant. Diamond thermal conductors for radiators and heat sinks in spacecraft. Diamond semiconductors for radiation-hard electronics that don't degrade in high radiation environments. Diamond optics for telescopes and scientific instruments. Phononic devices. Diamond's ability to propagate acoustic waves. Phonons. With minimal loss could enable phononic devices. Devices that manipulate sound waves at small scales, analogous to how photonic devices manipulate light. Applications might include acoustic sensors, signal processing using sound instead of electricity, thermal management using acoustic waves, biomedical implants. Beyond the biosensor applications already mentioned, diamond could revolutionize biomedical implants, diamond-coated joints and bone replacements, diamond electrodes for neural interfaces, brain-computer interfaces, diamond scaffolds for tissue engineering, diamond-based pacemakers or other implanted electronic devices. The challenge with many implants is that they must function inside the body for years or decades, resisting corrosion, immune reactions, and mechanical stress. Diamond's biocompatibility and chemical inertness make it ideal. Diamond photonics. While diamond is transparent to visible light, it's not often used for optical applications because of its high cost. But as lab-grown diamond becomes cheaper, new optical applications might emerge. Diamond optical windows for harsh environments, diamond nonlinear optical devices, diamond optical waveguides for integrated photonics. We started with a simple question: how can diamond and graphite be the same element? The answer is structure. How the atoms are arranged determines everything. This principle applies far beyond carbon. Every material is just atoms arranged in a specific way. Proteins are atoms arranged to perform specific functions. Semiconductors are atoms arranged to control electrical current. Crystals are atoms arranged in regular patterns. Amorphous materials are atoms arranged randomly. If you want to understand why a material does what it does, you have to ask, how are the atoms arranged? Diamond is remarkable because its structure is remarkably simple. Every carbon bonded to 4 others, tetrahedrally arranged, creating a 3-dimensional lattice. This simple structure produces extreme hardness, extreme thermal conductivity, extreme everything. As we engineer new materials, new semiconductors, new composites, new quantum devices, we're really asking, how should we arrange atoms to get the properties we want? Diamond is the answer to that question for many applications, not because diamond is magic, but because its structure, simple, rigid, highly connected, produces properties that are useful. And as technology advances, as we develop new synthesis methods and new applications, diamond will become more important, not less. The same element that your pencil is made of, arranged one way, marks paper. Arranged another way, forms the hardest natural material. Arranged in yet another way, becomes a quantum bit for a future quantum computer. This is the lesson of diamond. Structure determines everything. Understanding diamonds also requires understanding how scientists characterize them, how we measure their properties and determine their quality. The 4 C's of gemstone diamonds. The diamond industry uses 4 criteria to evaluate gemstone diamonds: carat, color, clarity, and cut. These are commonly called the 4 C's. Carat refers to weight. 1 carat is 200 milligrams. The term comes from carob seeds, which were historically used as a reference standard because they're relatively uniform in weight. Weight doesn't directly determine value. A 2-carat diamond isn't worth twice as much as a 1-carat diamond. Due to scarcity of larger stones, the price per carat increases with size. A high-quality 2-carat diamond might cost 3 to 4 times as much as a comparable 1-carat diamond. Color refers to hue. Colorless diamonds, white diamonds, though they're technically colorless, are typically more valuable than colored diamonds, with some exceptions. A colorless diamond has no yellow or brown tint. The color is graded on a scale from D, colorless, to Z, light yellow. Most diamonds have some amount of color, typically from nitrogen impurities. Fancy colored diamonds, intense colors like fancy vivid pink, fancy deep blue, can be extremely valuable. Their value comes from the rarity of the color and the saturation of the color. Clarity refers to the presence or absence of inclusions and blemishes. An inclusion is an internal defect, another crystal, a void, or some other foreign material inside the diamond. A blemish is a surface defect. Clarity is graded on a scale from FL, flawless, no inclusions visible under 10 times magnification, to I, included, inclusions visible to the naked eye. Most diamonds have some inclusions. Flawless diamonds are rare and valuable. Cut refers to how the diamond is faceted, how the faces are positioned and proportioned. A well-cut diamond will maximize light return to the viewer's eye and create the characteristic sparkle and fire. Cut is graded on a scale from excellent to poor. A well-cut diamond will be more brilliant and more beautiful than a poorly cut diamond, even if the other characteristics are similar. Other characterization methods. Beyond the 4 C's, scientists use various techniques to characterize diamonds. Spectroscopy. Measuring how diamond absorbs and reflects light at different wavelengths reveals information about defects and impurities. UV visible spectroscopy can identify nitrogen centers, boron, and other features. Raman spectroscopy. The vibrations of atoms in the crystal lattice have specific frequencies. Raman spectroscopy measures these frequencies, confirming that the material is diamond and revealing information about strain, defects, and crystal orientation. X-ray diffraction. Passing X-rays through a diamond crystal creates a diffraction pattern that reveals the crystal structure and orientation. This confirms the diamond crystal structure and can reveal twinning or other structural features. Photoluminescence. Shining UV light on a diamond causes it to fluoresce, emit visible light. The wavelength and intensity of fluorescence reveals information about defects and color centers. Magnetic resonance. Some defects in diamond have magnetic properties that can be detected using electron paramagnetic resonance or nuclear magnetic resonance. This is particularly useful for detecting and characterizing nitrogen vacancy centers. Thermal properties. Measuring thermal conductivity reveals information about the quality and defect content. A diamond with fewer defects conducts heat more efficiently. Hardness testing. While diamond can only be scratched by another diamond or specialized tools, the resistance to scratching can be quantified using nano indentation, pressing a hard probe into the diamond under controlled force and measuring the depth of indentation. While diamond semiconductors are the most intensively studied carbon-based semiconductors, there are other carbon materials with electronic applications. Graphene. Electronics graphene, a single layer of carbon atoms in a hexagonal arrangement, has electrical properties that are quite different from diamond. Graphene is a semi-metal or zero-gap semiconductor, meaning electrons can flow through it without needing to cross an energy gap. Unlike in typical semiconductors, this makes graphene conductive, but also means it's hard to turn off completely. To prevent current flow, researchers have been working on creating a band gap in graphene so it can be used as a transistor, but this proves challenging. Despite this limitation, graphene has applications in flexible electronics. Graphene can be bent and twisted without breaking. Thermal management. Graphene conducts heat extremely well in 2D. Optical applications. Graphene can manipulate light in interesting ways. Composite materials. Adding graphene to other materials can improve their properties. Carbon nanotubes for electronics. Carbon nanotubes can be semiconducting or conducting depending on their structure. Semiconducting carbon nanotubes can be used as transistor channels with potential advantages over silicon. High thermal conductivity for heat removal. High current carrying capacity. Small size enabling dense integrated circuits. However, carbon nanotube electronics face challenges. Difficulty in controlling whether nanotubes are semiconducting or conducting during synthesis. Difficulties in manufacturing consistent quality devices. Need for sophisticated interconnect methods. Research programs at Intel and other companies have explored carbon nanotube transistors, but commercial deployment is not yet happening at scale. Hybrid carbon electronics. Rather than using pure carbon, researchers are exploring hybrid materials combining carbon with other materials. Graphene on silicon. Carbon nanotubes on silicon substrates. Diamond on silicon, though the lattice mismatch is challenging. These hybrid approaches aim to get the best properties of both materials. The performance of carbon combined with the manufacturability and maturity of silicon technology. Understanding how diamonds form, how carbon atoms organize themselves into the diamond structure is crucial for controlling the synthesis process. Nucleation challenges. Creating a diamond in the lab requires getting carbon atoms to organize into the diamond structure rather than some other carbon form, the graphite, amorphous carbon, etc. At high temperatures, graphite is often more stable than diamond from a kinetic standpoint. It forms faster. Diamond formation requires that carbon atoms arrange themselves in the specific tetrahedral configuration, which requires overcoming activation barriers. This is where seeds come in. A diamond seed provides a template, a surface that's already in the diamond structure. New carbon atoms can attach to this template, continuing the diamond structure. This is energetically more favorable than forming diamond from scratch. Without a seed, nucleation is more difficult. Carbon atoms are more likely to form graphite or amorphous carbon rather than diamond. This is an active area of research: how to nucleate diamond without a seed, and how to ensure the nucleation produces the desired crystal quality. Growth mechanisms. Once a diamond seed is present, growth can proceed through several mechanisms. Layer by layer growth. Carbon atoms attach to the growing surface, building up layer by layer. This is the primary mechanism in CVD. Spiral growth. Growth can spiral around defects or dislocations in the crystal, similar to how crystals sometimes grow in nature. Defect-mediated growth. The crystal might grow via the formation and movement of defects in the structure. The specific growth mechanism affects the crystal quality. Controlled, uniform layer-by-layer growth typically produces higher quality crystals than defect-mediated growth. Growth rate limitations. CVD diamond growth rates are limited by several factors. Diffusion of carbon species. Carbon-containing molecules must diffuse from the gas phase to the growing surface. This diffusion is slow at lower temperatures. Surface reactions. The reactions that incorporate carbon into the diamond lattice have specific rates that depend on temperature and reactant concentrations. Nucleation rate. If nucleation is too fast, you get many small crystals rather than one large, high-quality crystal. Optimizing growth rate means balancing these factors to maximize quality while maintaining reasonable growth speed. Expanded section. Environmental applications of diamond beyond industrial tools and semiconductors. Diamond has potential environmental applications. Water purification. Diamond electrodes can be used for electrochemical water purification. An electrical voltage applied across a diamond electrode can oxidize contaminants in water, breaking them down into less harmful products. Diamond electrodes are particularly useful because they're chemically inert. They won't react with the water or corrode. They have a high oxidation potential. They can break down difficult-to-degrade contaminants. They can be regenerated or reused many times. Applications include treating, industrial wastewater, groundwater contamination, landfill leachate, pharmaceutical residues in water gas. Sensing. Diamond-based gas sensors could detect various gases and pollutants. The surface of diamond can be functionalized to be sensitive to specific gases, and the electrical properties change when the gas is detected. Applications include air quality monitoring, industrial emission monitoring, safety detection of hazardous gases. Radiation detection. Diamond is radiation resistant and can be used as a detector for ionizing radiation. A diamond detector counts individual radiation events by detecting the charge carriers they create. Applications include medical imaging, X-ray and gamma ray detection, radiation monitoring, space missions, detecting cosmic radiation, high-energy physics experiments. Carbon dioxide capture. Some research explores using diamond or carbon-based materials for capturing carbon dioxide from the atmosphere or from industrial emissions. The chemistry is still being developed, but diamond's properties, high surface area, if used in nanoform, chemical stability, and controllable surface properties, could make it useful for this application. It's worth considering why diamonds, beyond their practical properties, have become so valued in human culture. Rarity and scarcity. Diamonds are rare. They only form under extreme conditions deep in the earth and only reach the surface under specific geological circumstances. This rarity creates psychological value. Humans value rare things. Part of this is practical. Rare things are harder to obtain, but part is psychological. We associate rarity with value and worth. A common stone has no market value. A rare stone can be priceless. De Beers understood this and controlled diamond supply to maintain an appearance of scarcity. Even though diamonds aren't actually that rare, more diamonds are produced annually now than ever before. The cultural association with rarity persists. Permanence and immortality. Diamonds last forever. They don't decay, don't fade, don't break under normal conditions. This permanence creates a psychological association with eternity and immortality. An engagement ring diamond is given as a symbol of eternal love. The fact that the diamond will last forever, potentially through centuries, makes this symbolism powerful. Death and entropy are fundamental facts of human existence. Diamonds, in their permanence, offer a kind of counter to this. A diamond endures when everything else, including people, passes away. Clarity and brilliance. The optical properties of diamonds, their clarity and brilliance, have psychological effects. A clear, brilliant diamond catches the eye, creates pleasure, draws attention. This is partly about the physics of light. High refractive index creates sparkle, but partly about psychology. We associate clarity with truth, brilliance with value. A diamond's properties make it psychologically pleasing to look at and hold. Cultural history. Diamonds have been valued for thousands of years. This long cultural history gives them weight and significance. A diamond connects the wearer to history, to tradition, to human civilization itself. The stories of famous diamonds, the Hope Diamond's curse, the Cullinan Diamond's journey through empires, the Koh-i-Noor's history add to their psychological value. Conspicuous consumption diamonds are expensive, visible, and beautiful. Wearing a diamond is a visible signal of wealth and status. This conspicuous consumption creates psychological and social value beyond the diamonds. Intrinsic properties. This is why a lab-grown diamond, chemically identical, physically identical, but cheaper and known to be lab-grown, carries less social status. The value of the diamond includes its price tag and rarity, not just its properties. This raises interesting questions. Should we value things based on their rarity and price, or based on their actual properties? Is a lab-grown diamond actually less valuable, or is its value simply judged differently by society? Understanding diamonds also means understanding why scientists care about diamonds and why the public should too. Diamonds as teaching tools. Diamonds are an excellent teaching tool for understanding chemistry, materials science, and physics. The diamond-graphite comparison teaches the fundamental principle that structure determines properties. Students can physically examine different forms of carbon and understand how the same element can have completely different properties based on atomic arrangement. Diamonds' optical properties teach about how light interacts with matter. The refractive index, dispersion, and fluorescence of diamonds are all physics principles that students can observe directly. Diamond synthesis teaches about chemical vapor deposition, chemical engineering, and thermodynamics. Understanding how to make diamonds requires understanding these foundational concepts. Diamond defects teach about quantum mechanics. Nitrogen vacancy centers and other defects exhibit quantum properties that are still being explored. Public engagement diamonds capture public imagination in ways that few other materials do. A diamond is simultaneously beautiful, valuable, and scientifically interesting. Museums often feature diamond exhibits, using diamonds to teach about geology, chemistry, physics, and history. The famous diamonds, the Hope Diamond, the Cullinan, the Koh-i-Noor, have stories that engage the public. The Smithsonian Institution's display of the Hope Diamond attracts millions of visitors annually. The combination of the diamond's beauty, its history, its scientific properties, and the mythology around it captures people's attention. This public interest in diamonds provides an opportunity for science education. Museums can use diamonds to teach advanced concepts in an accessible way. Ethical and environmental science. The issues around conflict diamonds and environmental mining impact teach important lessons about science and society. Science and technology are not neutral. They're embedded in social and ethical contexts. Understanding the full life cycle of a material, where it comes from, how it impacts people and ecosystems, how it's used, what happens to it, is essential. Technology offers solutions to problems it creates. Lab-grown diamonds offer an ethical alternative to mined diamonds. Informed consumers make better choices. Understanding conflict diamonds and environmental impact allows people to choose responsibly. These lessons extend far beyond diamonds to all technology and resource use. Future research questions. Diamonds remain an active area of scientific research with many open questions. Can we make diamond semiconductors competitive with silicon at scale? Can diamond quantum computing outperform conventional computing? What are the limits of diamond properties at extreme pressures and temperatures? Can we engineer diamond properties at the atomic level to create new materials? What are the limits of diamond growth rates using CVD? Can diamond play a role in solving environmental challenges like water purification or CO2 capture? What new applications of diamond will emerge in the next decade? These research questions drive scientific progress and keep diamond at the forefront of materials science. When I first held that piece of diamond and that piece of graphite and realized they were the same element, I didn't just learn a fact about chemistry, I learned a principle about the universe. The principle is that form and arrangement matter more than content. Two pieces of carbon, literally the same atoms, become entirely different materials based on how those atoms are organized. This principle extends far beyond chemistry. In biology, the same DNA can produce different organisms depending on how genes are expressed. In physics, the same particles can exhibit different properties depending on their state and arrangement. In society, the same people can build very different cultures depending on how they organize themselves. Understanding diamonds isn't just about understanding a pretty stone or a useful industrial material. It's about understanding the fundamental principle that structure determines function. Diamonds, in their perfect crystalline form, their hardness, their beauty, their ability to transmit light and create sparkle, are a physical manifestation of this principle made visible. When you look at a diamond and see not just its beauty, but its structure, the tetrahedrally bonded carbon atoms arranged in a rigid three-dimensional lattice, you're looking at the principle of structure determining properties made manifest. This is why diamonds matter. Not because they're valuable, though they are, not because they're beautiful, though they are, but because they teach us about the deep principles that govern how matter organizes itself and what that organization allows it to do. The same principles that organize carbon into diamonds also organize atoms into everything else, everything we see, everything we are. And if we understand those principles, we understand not just diamonds, but the fundamental nature of the material universe. We touched on diamond under extreme pressures, but let's explore this more deeply. Understanding how diamond behaves at extreme conditions teaches us about materials science and planetary science. Diamond at ultra-high pressures. When pressures exceed 400 gigapascals, 4 million times Earth's atmospheric pressure, even diamond becomes unstable. At these extreme pressures, carbon transforms into different crystal structures. One such structure is called stishovite-like carbon, or other exotic phases that only exist at extreme pressures. These phases have different bonding arrangements and different properties than diamond. The fascinating aspect is that these ultra-high pressure phases have been found in meteorites. These phases formed during planetary collisions and impacts, and have been preserved in rocks that landed on Earth. By studying these meteorites, scientists learn about the pressures and temperatures that existed during planetary formation and collision events. In the other direction, scientists can theoretically predict what phases should exist at even higher pressures using quantum mechanical calculations. Some of these predicted phases might be even harder than diamond, though they would only be stable at those extreme pressures. Diamond at high temperatures. We mentioned that diamond converts to graphite at high temperatures, but the timescale of this conversion is important. At 1000 degrees Celsius, the conversion is slow. It would take billions of years for diamond to significantly convert to graphite. At 2000 degrees Celsius, the conversion is faster. It might take millions of years. But at temperatures exceeding 3000 degrees Celsius, the conversion accelerates significantly. This is why industrial diamond tools used in high-speed cutting must be cooled. Without cooling, the temperature can rise, and the diamond can convert to graphite and lose its hardness. Diamond in radiation environments. Radiation can damage diamond by displacing carbon atoms from their lattice positions. A carbon atom hit by a high-energy particle can be knocked out of position, leaving a vacancy and creating a displaced atom. These defects affect the diamond's properties. Thermal conductivity decreases, color might change, mechanical properties might be affected. However, diamond is quite radiation resistant compared to many materials. Semiconductors like silicon are often more damaged by radiation than diamond. This is why diamond is being investigated for use in space applications and high radiation environments where other materials would be damaged. Thermal shock. Thermal shock, rapid temperature changes, can damage diamond. If a diamond is heated and then cooled rapidly, the differential expansion and contraction between the surface and interior can create stress. This stress can cause cracking or other damage, particularly along grain boundaries or defect planes. For industrial tools, this means avoiding rapid temperature changes. Gradual heating and cooling are essential for maintaining diamond integrity. Understanding where diamonds come from geographically helps understand diamond geology and human history. Indian diamonds. India was the world's only source of diamonds from ancient times until the 18th century. Indian diamonds were found in alluvial deposits in rivers, particularly in the Deccan Plateau region. Famous Indian diamonds include the Koh-i-Noor, now part of the British Crown Jewels, and the Hope Diamond, now in the Smithsonian Institution. Indian diamond production declined as deposits were exhausted and production moved to other regions. India was essentially depleted of economically viable alluvial diamonds by the 1800s. Brazilian diamonds. In the 1600s, diamonds were discovered in alluvial deposits in Brazil. Brazilian diamonds fueled the global diamond trade for about 200 years until Brazilian deposits also began to decline. Brazilian diamonds were mined using slave labor in brutal conditions. The human cost of Brazilian diamonds was tremendous. South African Revolution. In 1867, a diamond was discovered in South Africa, marking the beginning of the largest diamond rush. Large open-pit mines were opened, and South Africa became the world's dominant diamond producer. The discovery of diamond pipes, Kimberlite deposits containing diamonds, in South Africa allowed large-scale mining. The Kimberley mines became the world's largest diamond mines. South African diamonds were initially alluvial, then placer mining, panning in streams, then open-pit mining as deeper deposits were accessed. The Kimberley open mine grew to become one of the world's largest open pits, over 1.6 kilometers across and over 800 meters deep. Other major diamond regions. In the 20th and 21st centuries, other regions became major diamond producers. Russia. Diamonds were discovered in Siberia, and Russia developed large mining operations. Russian diamonds, introduced to the market in the 1950s, challenged De Beers' monopoly. Australia. Large diamond pipes were discovered in Western Australia, making Australia one of the world's largest diamond producers. Africa. Diamonds were discovered in numerous African countries: Zimbabwe, Botswana, Angola, Sierra Leone, and others. Diamond mining became economically important for several African nations. Canada. Diamonds were discovered in the Northwest Territories in the 1990s, creating the Argyle Mine and other Canadian diamond mining operations. Geographic distribution of kimberlites. Diamond-bearing kimberlites are found in specific cratons, ancient stable continental regions. The major kimberlite provinces are South Africa, the Kapval Craton; Russia, the Siberian Craton; Australia, parts of the Archean Cratons; Canada, the Canadian Shield. These cratons are ancient, some exceeding 3 billion years old, and have been stable for long periods, allowing diamonds to form and persist in the mantle. Kimberlite eruptions occur sporadically. Some cratons had many eruptions in the past billion years. Others have erupted only recently in geological time. The geographic distribution of diamonds reflects the distribution of ancient cratons and the history of kimberlite eruptions. Future diamond mining. As easily accessible diamonds become depleted, mining moves to more difficult and expensive locations, deeper deposits, more remote regions, more technically challenging mining. Some estimates suggest that at current mining rates, known diamond resources will last several more decades. After that, either new deposits must be discovered or lab-grown diamonds will completely dominate the market. Lab-grown diamonds, not requiring mining, are not geographically limited. They can be produced anywhere that has the necessary equipment and energy resources. This is one major advantage of lab-grown diamonds over mined diamonds. To truly understand diamond, we need to understand carbon's bonding behavior, because diamond is the result of carbon forming its strongest, most rigid bonding structure. Carbon's electron configuration. Carbon has 6 electrons, 1s, 22s, 22p2. The valence electrons, the outermost electrons that participate in bonding, are 4, 2, s, 2, 2, p, 2. These 4 valence electrons are available for bonding. Carbon typically forms 4 bonds, using all 4 valence electrons. Hybridization in diamond. In diamond, carbon undergoes sp3 hybridization. The 4 valence electrons occupy 4 hybrid orbitals, combinations of s and p orbitals that point toward the corners of a tetrahedron. These sp3 hybrid orbitals form single bonds with neighboring carbon atoms. The tetrahedral geometry ensures maximum separation between the electron clouds of neighboring atoms, minimizing electron-electron repulsion and creating a stable, strong bonding structure. The carbon-carbon single bond in diamond has a bond length of about 1.54 angstroms and a bond strength of about 350 kilojoules per mole. Hybridization in graphite. In graphite, carbon undergoes sp2 hybridization. 3 hybrid orbitals form in-plane sigma bonds, strong single bonds within the layer. The 4th p orbital remains perpendicular to the plane, forming weaker p bonds with neighboring atoms in the layer. The in-plane bonds are strong, similar strength to diamond's bonds, but the interlayer bonds are weak van der Waals interactions. This explains graphite's layered structure and its softness. The layers can slide past each other because the interlayer bonds are weak. Hybridization in graphene and nanotubes. In graphene, a single layer of graphite, the sp2 hybridization is similar to graphite, but without the interlayer stacking. The result is a 2D material with strong in-plane bonding but no stacking interactions. In carbon nanotubes, rolled graphene, the sp2 hybridization creates cylindrical structures with strong bonding in the tube walls but no inner tube bonding, unless the tubes are in contact. Comparative bond strengths. Comparing bond energies. Cc single bond in diamond, approximately 350 kilojoules per mole. Cc single bond in graphite, in plane, approximately 350 kilojoules per mole. Cc double bond in general, approximately 610 kilojoules per mole. Cc triple bond in general, approximately 890 kilojoules per mole. Van der Waals interactions in graphite, approximately 10 to 20 kilojoules per mole. The differences in bonding explain the differences in properties. Diamond, with its network of strong single bonds in all directions, is hard. Graphite, with weak interlayer van der Waals interactions, is soft. Carbon's versatility. Carbon's ability to undergo different types of hybridization, sp, sp2, sp3, and form different bonding structures, single, double, triple bonds, makes it extraordinarily versatile. This versatility allows carbon to form simple molecules, methane, ethane, etc., complex organic molecules, proteins, DNA, etc., polymers, crystals, diamond, graphite, amorphous solids, exotic structures, nanotubes, buckyballs, graphene. No other element has this level of versatility. Carbon can bond with itself in so many different ways that it forms the foundation of organic chemistry and biological life. Diamond is the ultimate expression of carbon's bonding versatility, the most stable, most rigid, most densely bonded form of pure carbon. We've explored diamonds from multiple angles: their atomic structure, their properties, their synthesis, their applications, their history, their psychology, their chemistry. All of these threads converge on a single insight. Structure determines properties. Diamond's tetrahedral bonding creates hardness, thermal conductivity, optical properties, and all the other extreme properties that make diamonds special. But graphite, with its layered structure, is soft. Graphene, with its 2D sheet structure, is flexible and conductive. Nanotubes, with their cylindrical structure, are strong and slightly conductive. Same element, different structures, radically different properties. This principle, that structure determines everything, is not unique to carbon. It applies to all materials, all matter. DNA is DNA because of how its atoms are arranged. Proteins are proteins because of how their atoms fold. Metals are metals because of how their electrons are delocalized through their atoms. Understanding this principle is the key to understanding materials science, chemistry, physics, and even biology. And diamonds, in their geometric perfection and extreme properties, are the clearest example of this principle. When you understand diamond, you understand not just a gemstone or an industrial material. You understand a fundamental truth about how the universe works. As we conclude, here's a summary of diamond's remarkable properties and how they compare to other materials. Hardness, 10 on Mohs scale. Highest natural material, about 10,000 megapascals in Vickers hardness. No naturally occurring material scratches diamond except another diamond. Industrial materials like cubic boron nitride approach but don't exceed diamond hardness. Thermal conductivity, 2,000 watts per meter Kelvin, about 5 times copper, 10 times aluminum. Highest thermal conductivity of any natural material except maybe graphene, which is only 1 atom thick, so not directly comparable. Optical properties, highly transparent to visible and infrared light. Refractive index of 2.42 creates high dispersion and produces the characteristic sparkle and fire of cut diamonds. Fluorescence under UV light in many diamonds. Electrical properties, insulator under normal conditions, becomes semiconductor when doped with impurities. Boron for p-type, nitrogen for n-type. Band gap of 5.5 electron volts allows high temperature operation. Mechanical properties, very brittle, hard but can crack along specific crystallographic planes. Cleavage occurs along octahedral planes. Extremely rigid, low compressibility. Thermal stability, stable up to about 3,550 Kelvin, the melting point. Can convert to graphite at high temperatures, but this is slow at moderate temperatures, more thermally stable than most semiconductors. Radiation resistance, more radiation resistant than silicon and many other semiconductors. Maintains properties even in high radiation environments. Chemical inertness, extremely inert. Diamond doesn't react with most chemicals. This makes it useful for hostile environments and for biomedical applications. Density, 3.52 grams per cubic centimeter, denser than most common materials, but less dense than metals like lead. Sound velocity. Diamond has the highest acoustic velocity of any solid material, allowing sound waves to propagate through it very quickly. Beyond the practical applications we've discussed, understanding diamonds provides insights into fundamental scientific principles and technologies of the future. Understanding phase transitions. Diamond graphite transformation is a classic example of a phase transition, where a material changes from one crystalline form to another under different conditions. Understanding these transitions is essential for predicting material behavior under extreme conditions, engineering materials with specific properties, understanding planetary interiors, Carbon chemistry changes at extreme pressures in planetary cores. Understanding crystal defects, defects in diamonds, nitrogen centers, boron centers, vacancies, are windows into how imperfections in crystal structures affect macroscopic properties. This understanding applies far beyond diamonds to all crystalline materials and semiconductors. Materials. Engineering diamond represents the frontier of materials engineering, attempting to create perfect materials with specific properties through controlled synthesis. The techniques developed for diamond synthesis are applicable to making other super-hard materials and high-performance materials. Quantum science nitrogen vacancy centers in diamond represent one of the most tractable systems for studying and manipulating quantum effects. Understanding these quantum systems in diamond is advancing quantum science and quantum technology. Space technology. As we push further into space exploration, we need materials that work in harsh environments, extreme temperatures, high radiation, vacuum. Diamond's properties make it an ideal candidate for advanced space materials. Energy applications, diamond semiconductors, and diamond's high thermal conductivity make it valuable for energy applications. Power electronics for renewable energy systems, heat dissipation in concentrated solar power, high efficiency power conversion. These applications are not theoretical. They're being actively developed by research institutions and companies worldwide. Why this matters to you: understanding diamonds, understanding how structure determines properties, understanding how extreme conditions create rare and valuable materials, understanding how laboratory-created diamonds can match and exceed natural diamonds, teaches lessons that apply far beyond gemstones and industrial tools. It teaches how science works, how we discover new materials, how we manufacture them, how we test them, how we apply them to solve real problems. It teaches that things are not what they seem. Diamonds are beautiful to look at, but their beauty comes from quantum mechanics and atomic structure, not magic or mysticism. It teaches that human ingenuity can recreate what nature does. We can take simple carbon and recreate the conditions of the mantle in our laboratories, making diamonds that equal or exceed nature's products. It teaches that understanding is more valuable than simply accepting. Rather than just admiring a diamond, understanding what it is, the atomic arrangement, the bonding, the physics and chemistry, deepens appreciation and opens doors to using the material for purposes we haven't yet imagined. This is the real value of science education. Not just learning facts, but learning to see the world as interconnected systems governed by principles we can understand and apply. Diamond is one of the most beautiful objects in nature, but understanding the science behind it makes it infinitely more beautiful. We started with a simple observation. Diamond and graphite are the same element, but completely different materials. This observation opens doors to understanding not just chemistry, but physics, materials science, quantum mechanics, and the fundamental nature of matter itself. The lesson of diamond is that everything, absolutely everything, depends on structure. How atoms are arranged determines what they can do. This applies to materials. How atoms arrange themselves determines the material's properties. Biology. How molecules fold determines their function. Technology. How we arrange materials and structures determines what technology can do. Society. How people organize themselves determines what civilization can accomplish. The universe is not random. It's not determined by luck or chance or fate. It's determined by principles. Physical principles, chemical principles, biological principles. And those principles can be understood. Diamond is a reminder of this, a reminder that the universe is comprehensible, that complexity emerges from simplicity, that understanding is possible, and that understanding opens unlimited possibilities for the future. As of 2026, diamond science continues to advance with exciting recent developments. Lab diamonds for electronics. In 2025 to 2026, several companies and research institutions announced progress in diamond semiconductor devices. IBM demonstrated diamond MOSFETs with performance exceeding silicon in certain applications. Element 6 and Icon Semiconductor announced commercial diamond semiconductor products for specialized applications. These aren't revolutionary yet. They're niche applications where diamonds' unique properties provide clear advantages. But as manufacturing scales and costs decrease, these applications will expand. Quantum computing progress Google and IBM have published results showing that nitrogen vacancy centers in diamond can be used as quantum bits with properties comparable to other quantum computing platforms. The advantage of diamond is that these quantum bits can operate at room temperature, whereas many competing technologies require cooling to near absolute zero. 2026 saw initial demonstrations of quantum advantage in diamond-based systems. Calculations performed on diamond quantum devices faster than classical computers could perform the same calculations. These demonstrations are still in research phases, but they're moving toward practical applications. Lab diamond market growth. Lab-grown diamonds for gemstones have crossed a threshold of market acceptance. Major jewelry companies have begun offering lab-grown diamonds to consumers. The price premium for natural diamonds continues to decrease as consumers recognize that lab-grown diamonds are identical to mined diamonds. Market projections suggest lab-grown diamonds will dominate the jewelry market within 10 to 15 years, simply because they're cheaper. More years, simply because they're cheaper, more ethical, and more environmentally friendly. New synthesis techniques. Researchers continue developing improved methods for diamond synthesis. Recent work on plasma-assisted CVD, microwave CVD optimization, and hybrid synthesis methods has increased growth rates and improved diamond quality. Some researchers are exploring direct synthesis from CO2, extracting carbon from atmospheric carbon dioxide or industrial emissions, and converting it to diamond. If this could be done efficiently, it would create a direct path to carbon-negative diamond production. Industrial applications expansion. Industrial diamonds are increasingly used in advanced thermal management in high-power electronics, cutting and drilling in difficult geological formations, precision polishing in semiconductor manufacturing, research applications in materials science. As diamond becomes cheaper through lab production, more industrial applications become economically viable. Public engagement. Increasing museums and science centers are increasingly featuring diamond exhibits and educational programs. The Smithsonian's Hope Diamond draws millions of visitors annually. Other institutions have developed interactive exhibits where visitors can learn about diamond synthesis, properties, and applications. This public engagement is important for science literacy and for generating interest in STEM careers. I began this exploration with a professor showing me diamond and graphite and asking me to consider that they're the same element. That simple observation has led me through atomic structure, chemical bonding, extreme pressure and temperature, quantum mechanics, materials engineering, industrial applications, environmental ethics, and the fundamental principles of how matter organizes itself. And I've realized that this exploration doesn't end. Every time I learn more about diamonds, new questions emerge. How can we make diamond electronics scale up? What role will diamond play in quantum computing? Can diamond help us solve energy challenges? What will we discover next about diamond's properties under extreme conditions? This endless frontier of discovery is what makes science so compelling. We've understood diamonds for decades, but we're still discovering new things about them. We're still finding new applications. We're still pushing the boundaries of what's possible. And that's the real value of scientific investigation. Not the final answers, but the endless process of asking better questions and seeking deeper understanding. A diamond is just carbon atoms arranged in a specific way. But understanding those atoms and how they're arranged opens doors to understanding everything from extreme pressures in planetary cores to quantum computers that might solve problems we haven't yet imagined. This is why we study diamonds, not just because they're pretty or valuable, but because they teach us how to think about the world. They teach us that complexity emerges from simplicity, that extreme properties come from specific structures. That understanding is possible, and that understanding changes everything. To fully understand diamonds within the broader context of carbon chemistry and materials science, let's consider how diamonds fit into the periodic table and the landscape of carbon-based materials. Carbon is element number 6. It sits in the middle of period 2 of the periodic table between boron and nitrogen. This position gives it 4 valence electrons, not too many, not too few, making it extraordinarily versatile in bonding. Most elements are relatively straightforward in their chemistry. Hydrogen forms simple molecules. Oxygen forms oxides and water. Nitrogen forms amines and nitrides. But carbon seems to do everything. Carbon forms simple molecules, methane, CO2, complex organic molecules, thousands of natural products, polymers, plastics, proteins, DNA, crystals, diamond, graphite, amorphous solids, coal, charcoal, exotic nanostructures, nanotubes, graphene, buckyballs. No other element has this versatility. This is because of carbon's specific electron configuration and its ability to form strong bonds with itself and with other elements. Diamond is the most extreme expression of this versatility, the most densely bonded, most rigid form of pure carbon. It's the endpoint of carbon's bonding versatility pushed to the maximum. But diamond isn't the only important form of carbon. Graphite is essential for lubricants and electrical applications. Graphene is crucial for nanotechnology. Carbon nanotubes are important for materials science. Charcoal and activated carbon are essential for water purification and gas adsorption. Each form of carbon serves different purposes. Each has different properties because of its different structure. Understanding this, that the same element can be extremely versatile depending on how it's structured, is the fundamental insight of materials science. And it explains why carbon is so important, not just because diamond is pretty or valuable, but because carbon's versatility means it shows up in every major area of technology. Energy, carbon fiber, graphite, diamond electronics, medicine, diamond sensors, diamond implants, computing, diamond semiconductors, quantum systems, and environmental applications, carbon capture, water purification. The future of technology is likely to involve even more carbon materials and even more creative uses of carbon's structural versatility. Diamond will play its role in this future, not as the most important carbon material, but as one of many increasingly important carbon-based technologies that will shape the 21st century and beyond. This is why understanding diamond matters, because understanding diamond is a gateway to understanding carbon, and understanding carbon is a gateway to understanding materials, technology, and the future. Diamond represents the heights of what carbon can do. In that height, we see the possibilities of what any element can achieve when structured properly. And that lesson applies everywhere in science and technology. The lesson of diamond extends to every field of science and technology. In biology, the structure of DNA determines heredity. The structure of proteins determines their function. A single amino acid changed, just one out of hundreds, can completely alter a protein's function or create a genetic disease. Structure determines everything. In physics, the structure of atoms determines elements' chemical properties. The structure of crystal lattices determines whether a material is magnetic. The structure of spacetime determines gravity. Structure determines everything. In neuroscience, the structure of neural connections determines cognition and personality. A few neural pathways rewired, through learning, through experience, through injury, can change who you are. Structure determines everything. In technology, the structure of transistor gates determines computing speed. The structure of optical fibers determines data transmission. The structure of buildings determines their stability. Structure determines everything. Throughout nature, throughout science, throughout technology, we find the same principle. Structure determines function. Diamond is simply the clearest, most beautiful example of this universal principle. A diamond crystal is a physical manifestation of the principle that form determines substance, that arrangement determines properties, that structure determines everything. This is why diamonds matter, not just as gemstones or industrial materials, but as teaching tools, as reminders, as physical evidence of a fundamental truth about reality. When you look at a diamond, you're looking at atoms arranged in a specific pattern. You're looking at the physical embodiment of the principle that structure determines everything. And when you understand that principle, when you really grasp it, not just intellectually, but viscerally, it changes how you see the world. You start to ask different questions. Not, what is this? But how is it structured? Not, does it work? But why does its structure allow it to work? This shift in perspective is the real gift of scientific understanding. Diamond teaches this lesson perfectly because it's simple enough to understand. Carbon atoms bonded tetrahedrally, but profound enough to illuminate entire fields: materials science, chemistry, physics, quantum mechanics. So we study diamonds not just to understand diamonds, but to understand reality itself. And that understanding is the most valuable thing we can gain from science. Thanks for watching this deep exploration of the science of diamonds. May it change how you see the world, and may you find the same wonder in understanding matter that I have found. Diamonds are the only common gemstone that's literally indestructible. Rubies can be broken, emeralds can be scratched, sapphires can fracture, but diamonds endure. They last forever. This permanence means that a diamond you own today might exist unchanged for millions of years into the future. A diamond given as a gift might be passed down through generations, through centuries. This gives diamonds a unique psychological power. They're not like other precious things that fade, tarnish, break, or disappear. They're permanent, eternal. This is perhaps why diamonds have become so associated with love and commitment. Love is supposed to be permanent, eternal. A diamond expresses this symbolically. A commitment that lasts forever, just like a diamond lasts forever. Of course, nothing is truly eternal in a literal sense. Eventually, even diamonds will be destroyed or transformed. The earth will eventually be consumed by the expanding sun. The sun will eventually exhaust its fuel. The universe itself will eventually reach heat death. But on human timescales, on the timescales of human civilization, diamonds are permanent. This permanence is real and meaningful. It's one reason why diamonds became precious to humans beyond just their rarity and beauty. They offer a tangible reminder of permanence in a temporary, changing world. And perhaps that's the deepest reason why we value diamonds. Not just because they're beautiful or rare or hard, but because they remind us that some things endure, some things persist, some things are permanent. In a universe of entropy and change and decay, diamonds stand out as symbols of permanence. This is the poetry of diamonds. The science shows us their structure and properties. But the psychology, the culture, the history show us their deeper meaning to humanity. We value diamonds because they're beautiful and useful, but we love diamonds because they're eternal. And that love, that deep human response to permanence and eternity, is perhaps just as important as the science. The complete picture of diamonds includes both the rigorous scientific understanding of atomic structure and properties, and the deep human meaning we assign to them. Both are true, both are valuable, both matter. Understanding diamonds completely means understanding both the science and the significance. It means seeing them as both a crystalline structure of atoms and a symbol of permanence. It means recognizing that science and meaning, objectivity and human experience, are not in opposition, they're complementary perspectives on reality. A diamond is atoms bonded tetrahedrally, and a diamond is a symbol of love and permanence. Both are true simultaneously. This integration of scientific understanding with human meaning is perhaps the most valuable perspective we can achieve, not just knowing how diamonds work, but understanding what they mean, not just appreciating their properties, but grasping their significance. This is the ultimate lesson of diamonds, that understanding reality fully requires both scientific rigor and human wisdom, both objectivity and meaning. And that integration is what makes science not just powerful, but profound. Thanks for watching this journey through the science and significance of diamonds. In the end, diamonds teach us this: the universe is comprehensible. Structure creates meaning, understanding changes everything, and the pursuit of knowledge, the endless quest to understand how things work, is the most human and most beautiful of all endeavors.